Hi, welcome back to another video. Today we're going to talk about valence electrons. These are the electrons that are available for bonding. So in this example, you have Einsteinium. So if you look at the outermost shell of this atom, there are only 2 electrons. It has 99 electrons total, but only 2 in the outer shell, which are the valence electrons, those used for bonding. So first definition, valence electrons are electrons in the outermost shell or outermost energy level. They are the electrons available for bonding. So in group 1, they all have 1 valence electrons. We can predict the number of valence electrons based on their location in the periodic table because the periodic table is arranged based on the electronic structure of those atoms. So group 2 has 2 valence electrons. These are the alkaline earth metals. Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5 valence electrons. Group 16 has 6 valence electrons. Group 17, the halogens, have 7 valence electrons. And group 18, the noble gases, have 8 valence electrons, except for helium, which only has 2 because it has a full shell, and since it only fills that first shell, that's only 2 electrons. The transition elements, the D block, tend to have 1 or 2 valence electrons. They're a little weird and they don't always behave the same. This is why when we actually get to naming things, there's some more specifics that we have to do with those. Lanthanides and actinides, the F block at the bottom, they all have 1 or 2 valence electrons. Kind of the same thing with the D block. It's a little bit weird. So, dot notations. An atom's valence electrons can be represented by Lewis dot notations. The Lewis dot notations for the valence electrons of the elements of period 2 are this. So lithium has 1 valence electron. So you put 1 dot. The best way to do this is actually to put dots going around in a circle 1 at a time on the 4 sides. Beryllium has 2 valence electrons. You can do opposites or on adjacent sides. That would work fine. Boron has 3. Carbon has 4. Nitrogen has 5. So you'll notice once we fill the 4, we start doubling up again. So oxygen has 6. We've have 2 doubles, and then 2 singles, 2 unpaired electrons, and 2 sets of paired electrons, or 2 pairs of electrons and 2 lone electrons. Fluorine has 7 valence electrons, so 1 unpaired electron and 3 pairs of electrons. Neon has 4 pairs of electrons. It's a noble gas. It's completely filled up, and so we really can't get any more electrons around that, not reasonably. So, your turn. Draw the following Lewis dot structures. Hydrogen. Hydrogen has 1 dot. Beryllium, 2 dots, and they can be on adjacent sides or on the same side. Adjacent sides actually is probably a little better. Fluorine has 7 dots total, 3 pairs, 1 lone. Oxygen has 2 pairs and 2 lone electrons. Sulfur, actually going to look the same as oxygen, but with an S instead of an O. You'll notice that one's above the other in the periodic table, and so they're going to have very similar electronic structures. Phosphorus, it has 1 pair and 3 lone, just like nitrogen does, which is just above it. Nitrogen, there you go. You'll notice that it doesn't really matter which side the pairs are and which side the unpaired electrons are. They can be on different sides as long as you have, like for nitrogen, 1 pair could be on any of those sides, and then 3 lone electrons need to be on whatever the other 3 sides are.